We are presenting our solution to the energy consumption forecasting challenge. Given only historical energy consumption data and weather information nearby the building, we developed a deep neural network model to predict the consumption 24 hours ahead, and we choose RMSE as our loss criteria.
We can directly use the 5-row dataset, so there are 4 steps of data preparation. First, we split columns and merge the 5 datasets into one data frame as shown. Second, since these are raw datasets, there are missing values. It's necessary to fill up the missing values. Here, linear interpolation is used to fill up the data hole. Third, the energy consumption can also be influenced by the day of week, whether it's weekend and whether it's holiday. Therefore, to make the prediction more reliable, the 3 columns are introduced. Finally, we split the whole data frame into and tests are 7-3. Data normalization is efficient in reducing data redundancy and improve data integrity, and different methods can influence the model significantly. Based on experiments, we choose max-min normalization method to normalize the data. For persistent model, we use the naive approach, setting the predicted feature value equal to the observed present value, and get the persistent loss as 0.2118.
Observe the overall consumption trend. We find out that the first part of data is abnormal, significantly different from the rest. Then we remove them for the future training. We also plot autocorrelation graph of the raw data. There is a peak around 96, showing a cyclic trend in the data. We analyze the average data by the hour, date of week, and month. We can see that it is high between 8 a.m. to 8 p.m. during weekdays, suggesting this building is in an office or factory buildings. And we go on to analyze the monthly data. There's high consumption rise in the winter and mild rise in the July. There's an annual temperature between 23 and 28 degrees Celsius, suggesting that it is a mid-latitude regions. And there are 3 parts of feature engineering we are looking into it. So for the sliding window features, we include statistical and difference data inside.
I'm going to talk about the model training. We conducted different experiments, and it turns out that window sizes is more important. And we finally decided that the window size to be 96. From the lag graph, we can see the lag peaks at 96, which is good, but the line plot shows the forecasting is not satisfactory. During the experiment, we find adding batch normalization is important because the gradient may disappear. Showing this graph may disappear during the back propagation, and adding batch normalization can improve and help the loss decrease. The next experiment set, we try difference network. This is the first difference of the time series, and the test error is dropped by 50%. Differencing can help forecasting because it removes the seasonality of the time series. Inspired by such idea, we wonder if taking a second difference helps. It turns out that second difference is not helpful. Compare different feature settings and the activation function as well as the number of hidden neural numbers. We find that window size is better to be 96, and the activation function in this case, we have leaky ReLU and p-ReLU, which are better than the ReLU functions. We also do the experiments on optimizer. We compare stochastic gradient descent with momentum and Adam. It turns out Adam is better, and we adjust the learning rate accordingly. To avoid the overfitting, we add dropout and use early stopping, also adding the L2 regularization to reduce the overfitting. And our final structure is this one. This is a deep forward network with 3 hidden layers, each layer with batch normalization and some layers with dropout. Learning rate is 0.009. And the result of our model is shown in this graph. The train loss and the test loss is dropping. The test loss can be 0.10. And this is the forecasting series. As we can see, the forecasting series is better in this case. This is the test lag. The left side is the original dataset, and the right side is our models. As we can see, the model has the lag correlation peaks at 96, which is good.
So for model optimization, the first thing is learning rate selection. You can see in this graph, we can find the value of the learning rate, which corresponds to minimal loss. However, due to overfitting and data explosion phenomenon, we often go one order of magnitude before to choose the suitable learning rate to improve the model performance and persistence. Next is the min-max scaler. Why we use this method? We use this method because when input data attributes have different scales, some may range from 10 to 300, but some may range from 1 to 1000. So overall performance of the model usually is unacceptable. Then we choose the interval from -1 to 1, and we plug into the formula, and we get a quite low loss. The next thing is the model compression for lag. Many parameters in the deep neural networks are actually over-parameterized. We delete some insignificant weights and rearrange the remaining weights to keep the same accuracy of the model. This method somehow reduces the size of the model and the number of layers of neural networks will make our model simpler, faster, and more stable.